Okay, welcome to the first colloquium, I guess, of the winter semester. And we're going to start it off. Our first speaker of the series is by Dr. Felipe Guzman. Got his PhD in experimental physics from the Max Planck Institute for Gravitational Physics and the University of Hanover. And he went on from there to NASA, to a postdoc there. He had a postdoctoral fellowship at NASA Goddard Space Flight Center. And then he went on and he was a senior research associate at the National Institute of Standards and Technologies. And recently he joined the faculty here at Optical Sciences, and we're very excited to have him here. Shortly before coming here, he was with the German Space Agency and collaborating with the University of Bremen. And in all this work, he's been doing a lot of really exciting things in measurement science. And I think a lot of the students have heard of LIGO and the big impact that's had. But some of you may not be familiar with other big science things going on with lasers and optomechanics like LISA and GRACE and other things like that that Felipe has been very much involved in and will continue to be. And so we look forward to hearing about that today. And he'll tell us about laser measurement science and optomechanical technologies. So thanks.
Well, thank you very much, Jason, for the introduction. I'm very happy to be here and happy for having the opportunity to tell you about my research. So this is basically just a splash of the research topics that I will be developing here at U of A. We'll be working on optomechanical inertial sensors. I'll tell you a little bit about our ideas of collaboration here internally within OSE, quantum optomechanical inertial sensors together with Del Wilson, also optomechanical lasers with Alexander Lorraine, and also some of the work that I've done in the past and that we'll continue to do here in Arizona regarding laser interferometry for LIGO, for space-based geodesy missions, and space-based gravitational wave observatory LISA. So I've divided my talk in a few sections. I'll start with a brief introduction and background on applications in astrophysics regarding LISA and LIGO. Then I'll move over to aspects of geodesy, touching based on GRACE and GRACE follow-on. Then I'll switch gears and talk about some of the optomechanical technologies that I've been developing over the past few years. And I'll close up with some applications regarding to inertial navigation and some of the other topics that these technologies could be applied to. So a brief background on general relativity and gravitation. So basically, over a century ago, Albert Einstein gave us a new model, a new way to see gravity. And that's basically that space-time is a geometric structure. And as you can see here in the animation, if you think of masses moving across the universe, accelerated masses, these masses essentially curve the space-time and produce ripples that we call gravitational waves. Here in this animation, we see a black hole merger. And basically, what gravitational waves give us is a new way to observe the universe. All the astronomy that has been done to date until 2015 was based on detection of electromagnetic waves. This way, we're actually detecting the contractions and expansions of space-time produced by large masses moving across the universe. So it's a completely different way to observe the universe. It's not depending on electromagnetic radiation. One of the advantages of this is that it's a very clean signal that we observe because it doesn't interact much with anything else like light does. However, given that this interaction is so weak, it's also very hard to detect. And I'll touch base on that a little later. Now, something that happened in 2017, fairly recently, was the first detection of multi-messenger astronomy. And this is basically observing gravitational waves together with electromagnetic counterparts. Basically, when black holes merge or neutron stars merge, it's not just a gravitational phenomena, but also electromagnetic radiation is being released in that moment. So this allows us, the fact that we can observe both phenomena simultaneously allows us to learn so much more about the cosmological events that are happening. So this animation shows the merger of black holes and the related gamma ray bursts to that. We use laser interferometers to detect gravitational waves. So here in this picture, you can see an array of test masses in the circles. And basically, if you imagine a gravitational wave traveling towards the screen, what you're going to see is that the separation between these test masses will start contracting and expanding to the frequency of the gravitational wave. So if you imagine that we place a laser interferometer in this array, as shown here in the animation, basically when the masses start to move because of the gravitational wave, we'll detect a signal here at the black port, at the dark port of the microsome interferometer. So this is basically the concept of LIGO. Currently, we have a worldwide network of gravitational wave observatories. The 2 LIGO detectors here in the United States. We have 2 in Europe. Well, essentially, actually 1, which is VIRGO. We have a test bed called Geo600 in Germany. I don't know if you read in the news a few days ago, Nature, that actually LIGO India, or as they call it, Indigo, has received a green light to start construction. So basically what this is the old platforms from the first version of LIGO have been transferred to India and will be set up there, giving us basically more sky coverage for gravitational wave observations. And at the moment, there's another facility being built in Japan. So this plot gives you the strain sensitivity of advanced LIGO. LIGO is, I guess, the emblematic detector, so we're going to stick to this one for now. And what we can see here in the y-axis is the strain sensitivity, essentially the gravitational wave amplitude, which corresponds to the changes in length of the arm of the interferometer divided by the nominal length of the arm. So dl over L, essentially. And these are the observation frequencies. So this is the targeted sensitivity of advanced LIGO, something of the order of 10 to minus 23, 10 to minus 24 per square root of hertz. That was the design sensitivity. This is actually the current sensitivity of LIGO. H is, as I mentioned earlier, the amplitude of the gravitational wave, dl over L. And this gives us essentially a DL, so displacement detections of LIGO of the order of 10 to minus 20 meters per square root of hertz that we need to detect, or we need to achieve, in order to observe gravitational waves here on ground. This picture is the very first detection of the 2 LIGO detectors of the first event in 2015. You can see here very evidently the correlations of the signals of the 2 detectors. Something that we look in these detections is essentially that everything is right. I mean, that the time delay between detections is correct, appropriate to the path of a gravitational wave. When we observe these events, we want to essentially rule out effects of any other local activity that could perturb the detectors. This is why we need more than one on Earth. For space applications, this is not the case. There are, of course, plans to enhance the network of gravitational wave detectors by so-called third-generation gravitational wave detectors. These are essentially underground facilities of arm lengths in the order of 10 kilometers. We'll be using squeezed light to detect the motion of the test masses, larger beams, cryogenic environments, essentially all the points that you need to enhance sensitivity for a laser interferometric system. There are 2 concepts laying around at the moment. One is being developed in Europe. It's called the Einstein Telescope, ET, and one here in the US called LIGO Voyager. This chart here shows us essentially how the observation bandwidth of LIGO compares to LISA and how they complement each other. So as you can see here, LIGO essentially detects slightly above a hertz up to a few kilohertz. If you imagine of black holes that are spinning around each other at frequencies above a hertz, so these are very fast phenomena. They are moving very closely. And when you think of things spinning around each other at that velocity, it means essentially they're so close that they're about to merge. So, but of course they don't start there. There's been a process of evolution of the system to get to that point. And as the system evolves, the rotation period increases. So what happens at lower frequencies, and how can we observe it? that's the reason why we need LISA. We need to go to outer space. We need larger arm lengths. We need essentially interferometers that can fit the wavelengths of these systems to be able to observe other cosmological phenomena like supermassive black holes or galactic binaries, and essentially learn from those systems, but also be able to know when one of these sources will be able to enter the realm of LIGO detection. So for example, here in blue, this is the LISA sensitivity curve. Here in blue is the signal corresponding to the first gravitational wave detection back in 2015. So basically, if we would have had LISA already operational, we would have been able to tell LIGO, okay, look, pay attention to these days, because then you're going to be able to observe something. And this is a great capability that will enhance what I mentioned before, the multi-messenger astronomy, because then we can alert all the ground space-based electromagnetic telescopes to observe to a particular point in the sky. LISA, I mentioned that already in a few slides ago, is the Laser Interferometer Space Antenna. It's a space-based gravitational wave observatory. It's targeting observation frequencies between 10 to the minus 4 and 10 to the minus 1 hertz. It has an interferometer arm length of the order of 2.5 million kilometers. So basically, the separation between this spacecraft here is 2.5 million kilometers. It rotates around the sun, following the Earth, and is essentially a collaborative mission between ESA, the European Space Agency, and NASA. Initially, LISA was thought as a 50-50 partnership. However, due to budget constraints, a few years ago, NASA had to drop out of the collaboration. They just rejoined, and now it's essentially an ESA-led mission with some NASA contributions. But, well, it is still happening, and we're all very excited about this. This is essentially the orbit of LISA. The constellation consists of 3 spacecraft in an equilateral triangle, separated by 2.5 million kilometers, and they're following the Earth at a distance of about 19 to 23 degrees. That is approximately 50 million kilometers away from the Earth. This distance is chosen such that, it's essentially a compromise. You want to be so far away from the Earth as possible to avoid the gravitational disturbances from the Earth and the Earth-Moon system. However, if you're too far, then it'll be difficult to get the data. So you have to find a good compromise for this. As you could see here in the animation, the constellation was rotating. Basically, this rotation of the constellation provides us an antenna pattern that allows us to scan the sky and be able to locate the sources of the gravitational waves much more precisely. Well, I mentioned that the separation of the spacecraft is 2.5 million kilometers. However, as you can imagine, in celestial mechanics, those aren't exactly 2.5 million kilometers all the time. They are changing by about 1% over the course of a year. So if we want to measure very high displacement changes between gravitational sensors in each spacecraft, and for LISA, that is the order of picometers, we need to find ways to cope with this. Now, what plays in our favor in this case is that the period for this 1% change is 1 year. So it's significantly below the detection bandwidth for LISA. Now, it poses a challenge because this change also induces a Doppler shift on the lasers that we use to detect, to operate the interferometer. So this Doppler shift is of the order of 10 megahertz. So we basically run a phase lock loop to lock the interferometers and track that bit note that is changing because of this. This is just a view of what's inside the LISA spacecraft. So we have a telescope here that essentially collimates or prepares the beam to be sent out to the far spacecraft, but also receives the beam that is incoming from the other spacecraft. We have an optical bench that is essentially the interferometer, the local interferometer, to measure the motion of the test mass that is located here. And we also have what we call the moving optical subassembly. So if we have a triangle, and you can imagine that you're pointing the laser beam towards a far spacecraft, and that laser beam is traveling 2.5 million kilometers, you essentially have a delay of about 8 seconds. So you need to be able to point the laser not to where the spacecraft is currently at, but for the spacecraft is going to be in 8 seconds. So for this reason, we have an articulated system that moves the system of two telescopes to point the lasers accordingly. This system here. Just play this video. So this basically just shows the chain of sending the laser beam to the far spacecraft and receiving the laser beam from the far spacecraft. Space qualified lasers aren't as powerful as the lasers that we can operate here on Earth. So the maximum power that we're going to have from for a laser flying on LISA is still in the order of 1 to 2 watts. Now, in order to travel that distance, we increase the beam size from the optical bench, which is about 2 millimeters, to a size of about 30 centimeters to reduce the divergence for that travel. Still, once the laser beam reaches the far spacecraft, its diameter has grown to about 20 kilometers. That's just because of the Gaussian propagation over such a long path. And that, of course, induces a very strong power loss of the beam that is detected by the far spacecraft. So the 1 to 2 watts optical power that we're able to send out become about 100 picowatts. So what we do is essentially we play with the local oscillator, with the laser that is locally placed in each spacecraft, and increase its power such that we obtain a bit node that is detectable. So we have a low power from the incoming beam, but if we're able to increase the local power, then the product of the bit node essentially increases its signal. So that's how we manage to operate the interferometer this way. As you can imagine, this has several challenges. One is we need to fly these gravitational sensors, the test masses, with acceleration noise levels at or below 10 to the minus 15 meters per second squared. They need to be very still, and they need to only react to gravitational phenomena. The other challenge for LISA is essentially operate laser interferometers at picometers per square root of hertz, which is doable, but at millihertz frequencies. And one of the challenges here is essentially that you need to fly the interferometer, and you're never going to be able to see it again. So you have to make sure that everything is aligned properly, that it's going to stay aligned properly, and that you have all the measures necessary to recover the signal from the interferometer. And last, also the fact that we need to operate what we call micronewton thrusters on each spacecraft. So we operate LISA in what we call a drag-free mode. Basically, the test mass is sitting inside the spacecraft, and the satellite is wiggling around, shielding it from non-gravitational disturbances. For that, we need then the thrusters that drive the spacecraft that way. Because of these technological challenges, we decided a long time ago to fly the mission LISA Pathfinder. And the idea of LISA Pathfinder is essentially to pack one arm of LISA into a single spacecraft. So we compressed the 2.5 million kilometer arm of LISA into a space of about 30 centimeters. And in that spacecraft, we operate laser interferometers with the right precision required for LISA, picometers per square root of hertz at millihertz frequencies. We fly micronewton thrusters and also drag-free test masses that should come close to the levels of acceleration noise required for LISA. LISA Pathfinder was also flying 2 experiments, a European one and an American one. It's, as I mentioned, a single spacecraft. It flies 2 test masses as a single arm of LISA with micronewton thrusters and control laws, obtaining signals from the interferometer to control the spacecraft. This is an actual photograph of the flight model of the spacecraft before it was populated back in 2010. And this is just a CAD model of what the LTP, the LISA technology package, which is the main experiment flying on LISA Pathfinder, consists of. We have 2 test masses, an optical bench in the middle with laser interferometers to detect essentially the acceleration noise of these 2 objects. Again, just to give you an idea of the constellation, sets of thrusters that use the signal from the interferometers and control laws that drive the thrusters to make sure that we obtain a drag-free operation in the spacecraft. For LISA Pathfinder, we use a neodymium YAG laser. It's an EMPRA, a non-planar ring oscillator, running at 1064 nanometers. And the maximum power of this laser is 45 milliwatts. We operated the laser at about 38 milliwatts. The laser interferometer is a Mach-Zehnder interferometer split into 2 modules. One is what we call the modulation bench, consisting of the laser unit, beam splitting optics, acousto-optic modulators that shift the frequency of each individual beam by about 80 megahertz, and a little bit. The idea of this little bit, in one case is 500 hertz up, 500 hertz down, is to obtain a beat note at 1 kilohertz at the optical bench when the 2 beams interfere. The optical bench consists of 4 non-polarizing Mach-Zehnder interferometers. One interferometer is what we call the X12 interferometric or X12. Measures, you can see the beam here coming out from this Fibre injector and measures essentially the displacement between the 2 free-floating test masses. The X1 interferometers measures the displacement of 1 test mass with respect to the optical bench. We have what we call the reference interferometer that basically is fully confined to the stable optical bench and gives us a reference phase. Basically, everything happening before this point is common mode noise that will couple into all the measurement interferometers, and then we can easily take the signal of this interferometer and subtract it out from the measurements. We also have one ancillary interferometer. We call it the frequency interferometer, and it's an unequal arm interferometer that essentially acts as a delay line. So basically, it enhances the laser frequency noise, which is one of the major noise sources in the interferometer, and provides a signal that we use to control the laser frequency. So here in the optical bench, it looks almost as their equal arm. The difference is in the optical fibers here. The length of the optical fibers differs by about 30 centimeters. As you can see also here, one arm is much shorter than the other one, and those measurement interferometers are designed such that the difference in arm length between the 2 beams is in the order of about 10 microns. We were able to test all the bits and pieces for the interferometry of LISA Pathfinder on ground. So we started back in 2003 defining the specs for the laser, for the AOMs, for the optical bench, for the computer, for the phase meter, and so on. And from those breadboard components, sometime in 2008, 2009, we started receiving what we call engineering model units and flight model units that we integrated in our lab, tested one by one, but then also as a full system to operate the full LISA Pathfinder interferometry in the lab. This is a photograph of the flight model optical bench. It's a zero-Dur base plate with few silica components that are hydroxide catalysis bonded onto the base plate. This is essentially ensures that it's a quasi-monolithic assembly. So I can talk to you about more about catalysis bonding if you're interested. Just let me know. But basically, there are covalent bindings that are built between the optical components in the base plate, such that they yield a monolithic system. This is an interesting experience. We had to take the optical bench and basically make sure that it was going to survive the launch. I mean, it has to operate in space. It has to be launched. And the way to do this is you attach dummy masses to the ends of the test masses and put it on a shaker. And basically, you just pray that it doesn't break. But it worked. So we were very concerned when we had to do this. But I mean, at the end of the day, these components are built in a way that they should survive these kind of stresses. They have to be launched. Part of the space qualification and performance testing on ground also included, well, assembling everything in the spacecraft. Basically, all the systems that we had in the lab had to be moved away, be integrated on a spacecraft. And the spacecraft here, as a whole, had to be tested in special facilities. We put this into this large vacuum tank. Just to give you an idea of dimensions, the diameter of the spacecraft is of the order of 3 meters. So we had here a vacuum chamber that is 6 meters in diameter, a thermal vacuum chamber. We put in the spacecraft there. The chamber also had special lamps that would simulate the sun to power up the solar panels, such that the spacecraft would operate on its own. In that environment, we were able to power up the LISA interferometer and also conduct performance measurements. And these are the results of these special measurements. This isn't particularly a quiet environment because there are many pumps operating and a lot of equipment required for this. So we were actually pretty surprised that we were able to meet the requirements for LISA Pathfinder, which are in the order of 6 picometers per square root of hertz at the millihertz frequencies. For displacement, the optical bench is equipped with quadrant photo detectors to measure the tilt and tip of the test masses. Sorry. And well, we use those signals also to control the test masses in a way that we maintain the interferometer aligned. The requirement for that angular measurement was in the order of 20 nanoradians per square root of hertz. We were able to measure almost 2 orders of magnitude better than that. And let me actually show you the reason for that. It's these two guys that were built at the University of Glasgow in Scotland. Those are monolithic fiber injectors, specially built for this mission. So, as I mentioned earlier, we had to build engineering models and then flight models. This is the flight model of the optical bench. There was an engineering model of the optical bench. We used commercially available components for that, essentially metal fiber collimators. And, well, we never got anywhere near this sensitivity. We were always at the cusp of the requirements. It was still working, but, well, that made a huge change. This is the sensitivity that we were able to measure in orbit. So just as a reference, here in red is what I measured back during thermal vacuum testing in that facility. Here in yellow is the performance of the interferometer while the test masses were grabbed. You can imagine you cannot launch free-floating test masses. You have to fix them, hold them still, launch everything, and when your spacecraft reaches a quiet point, then you release them. That's a whole different story. It's difficult and complicated. I won't go into that. But basically, this curve here is where the test masses were grabbed. So we're able to actually, while grabbing the test masses, have the interferometer aligned and measure the performance of it. And then, of course, we wanted to run the experiment. We released the test masses. And this is the noise. Essentially, it dropped by almost 2 orders of magnitude. So we went from a few picometers to about 30 femtometers per root hertz at higher frequencies. This trend here is actual test mass motion because of the gravitational effects in the orbit where LISA Pathfinder was launched to. So essentially, this is all the signal that I wanted to observe. When we convert those displacement measurements to acceleration, then this is what we obtain. A few months after launching LISA Pathfinder, we launched it on December 3rd, 2015. So essentially on April 2014, we already had enough data to do a first assessment of how the mission was going. We're way below the requirements set for LISA Pathfinder in terms of acceleration. We're almost reaching the LISA requirements, after almost another year of operations, we were able to iron out all the noise sources, all the problems with calibrations and errors, and so on, and get essentially a better measurement or a better determination of what is the acceleration noise in the test masses. And we were able to surpass the LISA requirements by a factor of a few. So this essentially gives us complete confidence that the concepts we've developed for this challenging part of LISA have been achieved. We know how to do this. We're confident we can launch LISA and it will work. Well, there are still several aspects of LISA that were not tested on LISA Pathfinder, given that we had to shrink one arm to about 30 centimeters. Those aspects are essentially the long baseline interferometry and also the phase measurement system. Essentially, can we measure microcycle? So microcycles in this case would correspond to picometers per root hertz. Can we measure microcycle phase shifts in such an interferometer over such a long baseline with a very strong Doppler shift in the signal? And well, we were lucky enough to have another opportunity to test this on a different platform. And with this, I'm shifting to the other aspect. I'm moving away from astrophysics and going to geodesy, and we'll talk about GRACE. For those of you that are not familiar with GRACE, GRACE is the Gravity, Recovery, and Climate Experiment. It consists of 2 spacecraft that are rotating around the Earth. And basically, the idea is that this pair is flying in it's almost a polar orbit around the Earth. And when the first spacecraft approaches a mountain, it feels the big lump of mass and gets accelerated towards it. At some point later, the second spacecraft will feel that lump of mass and it'll start accelerating towards that. So that means that the separation between the 2 spacecraft will change. Well, as the first spacecraft keeps traveling, it'll stop feeling the mass of that big lump, of that big mountain, and will reduce its acceleration. So the separation between the spacecraft will increase again. So basically, you can play that game all across the Earth and do a very precise map of what we call the geoid, the gravitational, the geometry of the gravitational field of the Earth, not the geographic, but gravitationally. It's pretty different. So this mission was launched back in 2002. It was working nominally on an orbit of about 500 kilometers with a separation between the spacecraft of 200 kilometers. It was originally designed for a lifetime of 5 years. It operated until 2017, giving us very useful information about the gravitational field of the Earth and the processes that happen in our Earth related to climate change. One aspect of that is, for example, I don't know if you recall, back in 2014, there was this cover page of Science magazine reporting on the drought in California. And basically, well, this is a result directly from GRACE that over the years monitored the changes in gravitational field in this particular area and detected the reduction of mass of underground water in this region. Well, thankfully, new measurements have shown that this is no longer the case. But so you can imagine how important it is to have these kind of measurements across the Earth, to be able to have quantifiable information of the reduction in polar masses, what's happening with the ice caps, where the mass is going, how is this changing. Because GRACE severely outlived its planned mission life, the scientific community essentially pushed forward to launch a mission called GRACE Follow-On. It was launched in May 2018. It's essentially identical to GRACE. GRACE uses a microwave instrument, depicted here in blue, to measure the distance separations between the 2 spacecraft. It does it with an accuracy of the order of a precision of the order of micrometers. It's not great, but sufficient to detect the gravitational phenomena we're interested in. And one of the changes, because we were essentially interested in not necessarily pushing new technology forward, but having continuity in the science data, the community decided to build a replica of GRACE. We were able, however, to push a technology demonstration package in this mission, which is a long baseline laser interferometer. And it is depicted here as a racetrack interferometer in red. So we have essentially a very similar LISA interferometer, Mach sender as well, launching one laser beam from one spacecraft to the other, operating in what we call a transponder scheme. Essentially, the laser beam from the master spacecraft is detected at the far spacecraft. It's replicated by a local laser and sent back to it. So it's not a direct reflection because we would lose too much power, so much that we would not be able to operate the system. Interesting aspects of this interferometer is the fact that we also operate at powers of the order of 100 picowatts. We are in fact using the exact same laser that was flown on LISA Pathfinder, a replica of it. The separation between the spacecraft. So the distance between these two spacecraft changes depending on the gravitational field in the Earth.
Distribution over, say, the state of California?
That's right.
Well, what's the spatial resolution?
Exactly, and that's actually a great point. I might come to that later. The spatial resolution is about 300 by 300 kilometers. So it's not very high. That is actually one of the main aspects in the community right now, having a way to improve the spatial resolution. So one of the issues with GRACE is it's flying in a polar orbit. It flies over each point on Earth about once a month. So you don't get too much information. You're essentially doing a static measurement of the gravitational field. You're missing all the dynamics that are occurring in that period of time. So one of the major pushes right now is finding a way to increase that spatial but also temporal resolution, having the possibility of getting data points more frequently, but also in a much smaller grid. However, you can imagine that in order to do that, you need more pairs. A mission like GRACE costs about $400 million, so cost becomes very quickly an issue. So one of the ideas in Europe, but also in the US, is to fly something they call NGGM, the Next Generation Gravitational Missions, which consists of two pairs. One in the same orbit as GRACE right now, and one in a little bit inclined orbit by about 45 degrees. Well, not a little bit, but so in an inclined orbit. And that will give you, or reduce this temporal resolution to about 1 point every 2 weeks. And I believe the spatial resolution gets reduced to about 100 kilometers squared. But still, it's not great. So we need technologies that would allow flying more pairs, but also not necessarily losing sensitivity of these instruments. One of the aspects that we were not able to test on LISA is, on GRACE for LISA, is the required sensitivity. So with the interferometer, we're not really targeting picometers per square root of hertz. We're targeting more like nanometers per square root of hertz. The microwave system gives you micrometers. The laser interferometer gives you nanometers. The main limitation there is laser frequency noise because of the long arm. But therefore, then the phase measurement system is not as challenging. I will talk about some of these potential technologies for those applications in actually the next few slides. We're getting there. So changing gears and talking a little bit about some of the sensor development that I've been doing in the last few years, optomechanical inertial sensors. So basically, if you think of a moving mass, so this is a monolithic system. Is essentially etched out from a single fused silica wafer, giving you a mass that is well constrained in one dimension, and essentially giving external acceleration fields, this mass will move back and forth. So this is very nice when you can make it such that this mechanical oscillator operates as a simple harmonic oscillator. And the reason for that is that the transfer function between displacement and acceleration is given here and is defined only by two parameters: the resonance frequency of the oscillator and the quality factor of the mechanical oscillator. And those are parameters that you can very easily measure. So some of the things that we've been doing is essentially integrate micro-optical sensors to detect the motion of this test mass here. We use either fiber-based or monolithic Fibre interferometers that will give us very high sensitivity measurements of the motion of the test mass. Another interesting aspect of this particular geometry, and the main reason why we didn't go for a drumhead oscillator or membranes and so on for this particular application at least, is the fact that the mechanical modes are very well constrained. So we're interested in this fundamental mode. Any other higher modes are occurring at frequencies that are much higher and very far away from the bandwidth that we'd be interested in. So if you look at the acceleration sensitivity in this kind of systems, you will have contributions from essentially the thermal noise of the oscillator and also the noise of the measurement, of the optical measurement. So thermal noise is defined here and depends essentially from what we call the MQ product and the resonance frequency. And when we look at the displacement measurement, we essentially need to convert the motion of the test mass to acceleration by the resonance frequency of the accelerometer. So if we were looking into developing, for example, a 10 kilohertz accelerometer that is targeting about 1 nanoG per square root of hertz, we want to have MQ products above a kilogram, but we would also need test mass displacement in the order of 10 to minus 18 meters per square root of hertz. So this is pretty challenging. So one of the things that is sometimes not easy to grasp is when people talk about accelerometers, let's say you want to have an accelerometer that measures 10 to minus 6 meters per second squared per root hertz. But the bandwidth is crucial in this case. So you cannot maintain the sensitivity over any bandwidth you want. And the reason is that if you want to realize this kind of acceleration measurement, say over a bandwidth of 10 kilohertz, it means that you would need a displacement sensitivity of your test mass in the order of 10 to minus 10 meters per square root of hertz. That's fairly easy. If you want to maintain that sensitivity over a bandwidth of 1 kilohertz, then this goes with the square of the resonance frequency. So basically you're constraining, or you're putting a higher requirement on your displacement measurement by 4 orders of magnitude. Correspondingly, the same, if you know that you can measure displacement with a given sensitivity, basically you can play with the bandwidth in order to make sure that you achieve your acceleration sensitivity in a particular regime. So these are some of the sensors that I've developed over the last few years. One of the things that I also like about this particular geometry is that it's very easily scalable. So here you see a photograph of a sensor that fits on a fingertip. This is a sensor that is slightly smaller than an iPhone 5. So basically about 9 centimeters by 4 centimeters by 3 millimeters. And you can do acceleration sensing over a wide range of applications, either vibrations at kilohertz or also gravitational accelerations at millihertz. I started this work while I was at NIST, and the main driver for that activity was to develop acceleration standards and force standards. that would help us increase the accuracy in which we can realize acceleration at this point. We would also then develop various types of fiber-based or micro-optical sensors to measure the displacement of those test masses. And as I mentioned, we were working also on force sensors, atomic force microscopy, and also looking into the possible accuracies that we can achieve with these devices, and also look into radiation pressure driven AFMs, calibration of laser power with optomechanical systems, and so on. This is just a little summary chart of the performance of the mechanics and the optics that we've shown in the past. We've achieved Qs with these little systems in the order of 10 to the 6. We've measured displacement with these micro-optical cavities in the order of 10 to the minus 16 per square root of hertz. In terms of primary standards for acceleration, it is kind of embarrassing how bad right now it's possible to calibrate accelerometers externally. So the accuracies that we can reach at NIST or PTV or any National Metrology Institute around the world are at best in the order of 10 to the minus 2 or 10 to the minus 3, 10 to the minus 3 relatively. So that's, when you think of frequency standards, for example, that's just embarrassing. So we're looking into ways on how to improve that bit by bit. This was part of that effort. So here you can see one of our accelerometers mounted on the primary facility at NIST. This is a shaker with a laser interferometer. I don't think you can actually see the laser beam here. There's an interferometer up on top that is being reflected off a little mirror that I mounted on the device to measure the motion when the shaker would go up and down. But then we would also have the little fiber optic device here that measures independently the oscillating mass here. And then we would compare the measurement from the external interferometer with our accelerometer here. And we were able to achieve accuracy in the order of 10 to the minus 3. Some tests even got to 10 to the minus 4. But basically, we were comparing the measurements from one system to ours. One of the major errors here that we realized from this particular test facility is when the system goes up and down, it doesn't do a rectilinear motion or a pure rectilinear motion, but it starts tilting as it goes up or down. And that's an error that currently those primary facilities cannot account for. So when the drum shaker goes up and tilts, well, the external interferometer is going to measure a signal that our little microcavity is not going to observe. So there is an error, but it's not necessarily an error on the measurement that we're realizing here, but it's more an issue of the facility. Right now, the colleagues at NIST are working on having measurement capabilities like, for example, the differential wavefront sensing system that we use in LISA Pathfinder to measure the angle, the tip and tilt of the test masses. They're looking into developing something like that here to be able to measure tip and tilt and correlate for those errors. Another interesting development that we did with these little devices was to include little piezoelectric systems on the sides of the sensor in order to, well, one, be able to scan the length of the cavity completely by a full free spectral range, but also to modulate the length of the cavity and be able to have high frequency, essentially an error signal that will let us lock these systems to a reference laser, for example, or to use this frequency modulation effectively of the cavity to read out the cavity as well. All of this essentially avoiding or bypassing complex high frequency electronics and electro-optics like EOMs because we have very short cavities in the order of 70 microns. You can imagine that for such a short cavity, your FSR is in the order of 14 to 20 nanometers. The modulation frequencies that you need to realize to do PDH, Pond River Hall, are in the order of several gigahertz. So all of that is overhead that, sure, you can do, but you want to avoid if possible. So this actually provided us a way to do something very similar with very simple components at megahertz frequencies. This is also part of the work that we were able to do with AFM sensors. We achieved Qs in the order of 4 million for these little devices here. We were able to measure femtonewton forces with these systems, and also with accuracies in the order of 10 to minus 3, which is actually unprecedented in AFM. They typically achieve errors in the order of 10% or 20%, which is also extremely high. Now, I guess coming back to your question about, how can we improve the measurements on GRACE? So GRACE, measures the gravitational field of the Earth by, as I mentioned, observing the separation between the spacecraft. But part of the payload that is contained on that spacecraft is not just the distance measurement system, but also accelerometers. And those are very heavy, very bulky systems of several tens of kilograms, several liters, that are designed to achieve very high or very low acceleration noise. Those are actually one of the drivers right now that constrain the sensitivity in GRACE. So part of what we want to do with these optomechanical systems is to get them to a point where they are comparable to the sensitivity required by the accelerometers on GRACE. However, with a form factor much, much smaller, with masses that are much lighter, that will enable the integration of these systems in spacecraft that are significantly smaller, perhaps not CubeSats, but still smaller, cheaper, and will enable then correspondingly flying constellations of more pairs. This is some of the ideas that we're currently pursuing, in fact, for optomechanical gravimeters and gravity gradiometers that are targeting acceleration sensitivities in the order of 10 to minus 11 meters per second squared per root hertz for acceleration, and gradients in the order of 1 EDVOS per hertz. For those of you not familiar with the EDVOS unit, this is basically 10 to minus 9 meters per meter. So yeah. So you're measuring the gradient of gravity. So you want to achieve 10 to minus 9 meters per second squared per hertz in one end, 10 to minus 9 meters per second squared per hertz on the other end, over a meter. That would correspond to an EDVOS. So we want to achieve that in form factors in the order of 10 centimeters to 15 centimeters. This chart gives you an idea of the acceleration sensitivity required for this type of applications. Here, up on top is the sensitivity from the GRACE accelerometers. This is the level that we're targeting with these optomechanical sensors. This is the level demonstrated by GOCHE, which is another geodesy mission. And this is LISA. This is a chart that gives you an idea of the actual characteristics between the sensors themselves. GOCHE has a test mass of the order of 320 grams. The GRACE accelerometers have a test mass of the order of 72 grams. We're targeting test masses in the order of 1 to actually 10 grams, perhaps 20. Total masses are in the order of 10 kilograms. For GRACE, it's on the order of several kilograms. We're looking at a total system of a few hundred grams. Comparable acceleration sensitivities, much lower power, and so on. That would enable precisely that flying constellation of satellites. Inertial navigation. So one of the major issues. Both. So you can essentially tune the orbit of the pairs in a way that you can sample the same location with a higher frequency, and there also get better temporal resolution, but also have more pairs that will give you more information or I guess a smaller grid. So reduce that 300 kilometers by 300 kilometers squared area that Grace is sampling now to something much smaller.
From a scientific point of view?
Yeah. Yeah.
Spatial resolution? Because I would think the temporal resolution, usually these are not instantaneous changes anyway.
That's true, but if you think of, for example, monitoring seismic activity, then in terms of climate, well, this is not just, I guess, climate change. There are many areas, but seismology could be one of them. You would also be interested, I guess, in terms of defense applications, detecting detonations. So those are very fast, localized events that a grid or a network like this would enable. So applications of these technologies for inertial navigation are, for example, the fact that, well, one of the major issues is operating in GPS-denied environments. So what happens when you're flying an airplane or even a ship, and suddenly your GPS system stops working? So how do you navigate? And this has actually happened in the past, where there was, I think a year or two ago, came out in the news of a ship off the Gulf of Mexico that was, the GPS system was hacked. So people thought they were navigating to a location where they were actually being steered towards a different location. And there was no way to verify that. So you rely completely blindly on what your navigation system is telling you based on GPS, but that can be hacked. However, inertial information is, there's no way to alter that. You're measuring, you're moving and navigating based on the gravitational environment that you have. That's only dictated by mass. So that is one of the main advantages of inertial navigation. And for that, then we also need systems that can give you better measurements, better positioning, but especially longer term and high stability measurements. So these type of sensitivities that we've measured in the past can potentially enable 10 to 100 meter absolute positioning over periods of time of 3 hours. This is something that is at the moment not doable, and is actually the target of several programs looking into developing these technologies. So we need very stable mechanics. We need very high sensitivity sensors to measure those mechanics accurately. And some of the figures that are relevant for this type of operations is what we call the bias stability, essentially the Allen deviation of acceleration over long integration times. So typically, this is what you get when we operate one of our sensors, for example, with a free-running laser. So the laser frequency is not locked. When we stabilize it, we can operate one of the sensors over several hundred seconds with a sustained high sensitivity below or around 10 to minus 6 Gs. Additional developments that we have started is development of fully monolithic systems precisely because of this. So we want to rely, or we want to take advantage of properties of the materials that we choose to develop these sensors. Basically low CT materials, low loss materials. We have started to incorporate the optics in the systems themselves. So this is essentially just what we call low finesse cavity, a finesse of 2, where the 2 mirrors are already designed into the fused silica chip. We can think of developing these devices into multiple degree of freedom sensors that are compact, providing also high sensitivity, giving you measurements in orthogonal axis precisely for the applications of inertial navigation. Then let me mention briefly some of the other applications that these technologies could do. For example, micro-optical motion sensors. We can use these low finesse cavities to measure targets over long displacements over long separations. Essentially, we don't need to stick or lock the system to a fringe. We can let the microcavity drift away. However, with modulation schemes, we can track the quadrature signals and still measure high sensitivity displacements of moving targets in industrial applications. Some of the sensitivities we're being able to demonstrate with these devices are in the order of 40 to 80 picometers, which is not one of the best that we've measured. However, the impressive fact here is the fact that we've measured this sensitivity over 6 decades of frequency. So we can maintain this fairly high sensitivity from millihertz all the way to kilohertz, which is relevant for many applications also in industry. You can imagine one of those applications being, for example, monitoring the LISA or Grace test masses and accelerometers. Atom interferometer and optomechanical sensors. I won't go into the detail of atom interferometers. However, what I want to mention here is for the last few years, there's been a lot of work by the community into developing atom interferometric systems as inertial sensors to measure gravity gradients, and also inertial navigation as well. And one of the major challenges that these systems face is the fact that they rely on an inertial reference, which is this reference mirror right here. So when this mirror is experiencing external vibrations and noise, it basically scrambles the face of the atom interferometer. And then you don't know where you are on the fringe anymore. So it's difficult to extract any sort of inertial information from there. What we've done, this is a project that I started back in Germany and that I'm continuing here, is basically merge that inertial reference with one of our optomechanical sensors. Essentially, this sensor will then sense the local seismic noise, and we can use the signal to correct the phase and basically reconstruct the phase of the atom interferometer. This is the sensitivity that we were able to achieve with this particular sensor. It's in the order of 10 to minus 7, 10 to minus 8 Gs, at not too high frequencies, between 1 and 100 hertz. But here is, I guess, the interesting result that we've been able to show recently. This trace here gives you the acceleration noise or the acceleration measurements of the atom interferometer when it's running freely, when no correction is being applied. Once we use the information from the micromechanical system to correct or reconstruct the phase of the atom interferometer, we can increase the sensitivity of this system by almost 1.5 orders of magnitude. So there are many, so the community, well, the experts in atom interferometry are developing these type of systems in all kinds of fashions. They're building towers of several meters high to measure, for example, equivalence principle or do very high precision gravitational measurements, but they're also producing BECs on chips, especially targeting those applications in navigation. However, this particular problem will take place in all of them. And this could be an interesting solution to be able to correct for that. Another project that I have launched since I got here in collaboration with Alexander Lorraine is the development of what I call optomechanical lasers. Basically, this is merging these same structures with a VXL laser, so a vertical external cavity surface laser. The main advantage here is that you can convert your optomechanical sensor into a laser itself and then measure the dynamics of your test mass through the frequency changes of your VXL. This will give you a frequency signal, which we know how to measure with very high accuracy, but also will allow you to get rid of the entire instrumentation overhead of having external lasers, fiber optics, and so on to operate these devices, because that device will be in itself a laser. Another of the projects that I've been working on lately together with Dal Wilson, is looking at the development of quantum optomechanical inertial sensors, basically developing high-quality mechanics, high-quality optics for many of the applications that I already discussed, targeting sensitivities in the nanoG per square root of hertz. And basically what we're looking to develop here is sensors that are at the quantum limit or that we can enhance through techniques of quantum cavity optomechanics, like ponderomotive squeezing to reduce the back action of the systems and increase in sensitivity. So lastly, I would like to acknowledge the members of my new group here at the University of Arizona. These are the grad students in my group. I've been collaborating, as I mentioned, with Dal Wilson, Alex Lorraine, and John Ellis. Christian is a PhD student actually in Dal's group that has been working with us. And with that, I'll like to thank you for your attention. And I'll be taking any questions.